Hi everyone, welcome back to our mini-series on Möbius inversion. In the previous lecture, we talked about the divisor sums. We started with a hidden function a, summed over all divisors to get bn, and show how the process blurred the information. Now, in this lecture, we're going to finally introduce the function mu. It is a tiny function that only takes values -1, 0, and 1. But it encodes just enough information about prime factors to let us undo those divisor sums later. Now think of this video as the definition and intuition episode. Once you are comfortable with mu n, the full Möbius inversion formula will feel natural. So what you're going to learn in this lecture is the definition of mu function from the prime factorization. We're going to talk about square-free versus repeated primes, the value 0 or plus minus 1. And we're going to practice reading mu straight from the factors of n. In the next lecture, we're going to plug mu n into divisor sum and turn it into a real inversion formula.
Last time, we built functions by summing over all divisors of a number. Now we want a tool that can reverse those divisor sums, and that tool will be a tiny function called mu that only ever outputs -1, 0, or 1.
So mu is not really measuring how big n is, it is more like a code for the structure of n?
Exactly. Mu looks at the prime factorization of n and returns a small value that remembers things like whether n is square-free and how many distinct primes it has. That structure is what lets us undo divisor sums later. The definition on this slide says three things. First, mu of 1 is 1. Second, if n is the product of k distinct primes with no repeats, then mu of n is -1 raised to the k, so the sign depends on whether k is odd or even. Third, if any prime square divides n, then mu of n is 0. That is where the square-free condition appears.
I want to be sure I get square free. It means in the prime factorization every prime appears at most once, right? And why do we choose mu of 1 to be 1?
Yes, square-free means no prime power, like p squared divides n. For n equal to 1, there are no primes at all, which we think of as 0 primes, an even number. Setting mu of 1 equal to 1 makes the sign rule consistent and also makes 1 behave like a neutral element for multiplicative properties we will use later. Now we add a powerful property. If m and n share no prime factors, then mu of m times n equals mu of m times mu of n. Intuitively, the prime blocks coming from m and from n stay independent in the product, so the square-free status and the sign for the product are just a combination of the two pieces.
For the example with 6, that means we factor 6 as 2 times 3, see that each prime appears only once, and since both mu of 2 and mu of 3 are -1, their product is +1, matching mu of 6?
Exactly. And notice why we insist that m and n are coprime. If they shared a prime, then in the product, that prime could appear with exponent at least 2, and the 0 or non-zero behavior would no longer be determined by the separate values mu of m and mu of n. So multiplicativity would fail without the coprime condition. Let us read this table using the rules. First, scan for numbers that clearly have a prime square in their factorization, like 4, 8, 9, 12, 16, 18, and 20. All of those get mu value 0. The remaining numbers are square-free, and for each of those, we just count how many distinct primes appear and assign -1 for an odd count and +1 for an even count.
Looking at the row, I see that 6 and 10 get +1, since each is a product of two different primes, while 12 and 18 are 0 because they include a squared prime. It feels like zeros are already starting to show up more often.
Good observation. As numbers grow, a positive fraction of them are not square-free, so zeros for mu appear regularly. Later in number theory 1 can show that the proportion of square-free numbers is about 6 divided by pi squared. But for now, just focus on how quickly you can read off mu from the factorization. Let us step back. Mu of n is completely determined by the prime factorization of n. If n is not square-free, mu is 0. If n is square free, the sign is negative when there is an odd number of distinct primes and positive when there is an even number. On top of that, mu is multiplicative for coprime inputs, which will make algebra with divisor sums much easier.
So once I know the primes of n, I never need to compute any divisor sums to get mu of n. I just inspect the exponents and count how many distinct primes appear.
Exactly. That is why mu is such a central object in multiplicative number theory. Next time we will plug this function into divisor sums and see how it lets us reverse those constructions from lecture 1. Try the 3 values on the slide. For 8, the factorization is 2 times 2 times 2, so there is a squared prime, and mu of 8 is 0. For 10, we have 2 times 5, 2 distinct primes, so mu of 10 is plus 1. For 15, we have 3 times 5, again 2 distinct primes, so mu of 15 is also plus 1. Then think about 21, which is 3 times 7.
Following the rule, 8 is not square free, so its mu is 0. Both 10 and 15 are square free with 2 primes, so their mu values are plus 1. For 21, it is also a product of 2 distinct primes, so I would expect its mu to be plus 1 as well.
Perfect. You used the definition in exactly the right way. The reflection question is there to remind you that mu is really a short summary of the prime structure of n. If you can quickly factor a number, you can quickly compute mu, and that speed will matter when we use mu inside more complicated formulas.
Thank you for your time in watching this. Please like, share, and subscribe to the channel. Of course, we always would like to hear from you. Please make your comments below.